Hi, my name is Sam.
And I'm Sam.
We're both part of Company 8 in experimental methods as part of the Aerospace Engineering Department. Our chosen topic of research this semester was to do a rear wing aerodynamic analysis of the newest design from the Formula SAE team for their 2021 to 2022 season. Using a simplified bluff body and a rear wing, we were able to acquire experimental data from the wind tunnels.
This forward model allowed us to correctly model the airflow over the vehicle that the rear wing will be experiencing. This rear wing was adjusted for 9 different angle of attack configurations, allowing us to collect data and extrapolate that data out to help our customer.
Using that experimental data, we were able to provide predictions for what configurations work best on different track types. Now let's go take a look at some of that data. Now that we are looking at the experimental data, let me walk you through how the graphs are laid out. Firstly, the element configurations consist of 15 degrees of angle of attack for the first element. The second element ranges from 0 to 15 to 30 degrees of angles of attack. And the third element ranges from 0, 25, and 50 degrees for an angle of attack. Because our model is at 30% scale, we are unable to match the loading cases of the full scale model without reaching breaking points of the model or the limitations of the mount that holds the model. Because we are limited by the loading of the model and the loading of the mount, we use Reynolds number, which is a dimensionless parameter, to relate the loading of the 30% scale model to the full scale model. Now that this is understood, I can review the experimental results that we acquired. It can be clearly seen on the downforce versus velocity graph that the most aggressive configuration, consisting of 15 degrees, 30 degrees, and 50 degrees angles of attack for each element respectively, corresponds to the highest downforce we can achieve. At 60 pounds of downforce on the 30% scale model, this corresponds to 140 pounds of downforce on the actual car. But what does this mean in terms of cost with drag?
The trade-offs in aerodynamics are clear from this graph. While in the previous slide shown by Sam, the highest lift was our 15-30-50 configuration, here it is at the bottom, showing that the ratio of our lift to drag is actually the worst configuration in terms of efficiency. Shown by this graph, the 15-0-0 configuration is our highest efficiency at just under 3.4, whereas our highest downforce given by the previous is at the bottom, showing that there's an inverse relationship between efficiency and maximum downforce. Taking that into consideration, we have to make recommendations to our customer. For example, during the skid pad event, downforce is needed. During the acceleration event, low downforce, high acceleration is key. And then for the autocross, we must strike a balance between the two. The large negative slopes shown at the top show that there is a dependence between coefficient of drag and Reynolds number, which tells us that there is a large amount of separation occurring for the higher angle of attack configurations.